So hello everyone, so welcome to the Quantum BC seminar. So we are happy to have Jeff McGuirk to be our speaker for today. So Jeff is an associate professor at the Department of Physics at Simon Fraser University. He is an expert of ultra-cold atom physics. So before joining SFU, so Jeff did his PhD at Stanford and Yale, and then after that he went to Gila to pursue a postdoc fellowship. And then at that time he worked on bose-Einstein condensate, very cold material. And after joining SFU, Jeff has established a research group focusing on the experiments using ultra-cold atoms to explore the roles of quantum symmetry in spin dynamics of trapped atoms. I think today he is going to tell us some more recent results about the quantum simulation with trapped atoms. Jeff, this is your stage.
Thanks, Kira. Hi, everyone, and hi, everyone online. I was reflecting as I was looking at this picture that those of you that have been around SFU for a while can kind of date pictures by how far the condo communities down here have been built into the parking lots. So I think this is from a few years back. Yeah, so I want to talk to you about work that we've been doing in my group, basically trying to understand and control the transport of spin in an ultra-cold gas. And the non-degenerate is kind of an interesting word there as well that we'll get into. So this kind of came together sort of by melding a couple of ideas. One is a more fundamental look at transport dynamics and diffusion and looking at the fundamental physics of ultra-cold fluids. And another is more device focused, and I'll kind of talk about how those came together here. So in the classical world, diffusion is a pretty well understood thing. We talk about heat, we talk about vehicles, we can talk about particulates. During the pandemic, all of us became armchair experts when we were stuck at home on the diffusion of aerosols, which is what that picture is about. And generally, the underlying physics is pretty well understood. It can be quite complicated to model based on, what sort of restricted geometries and things like that, and interactions that you want to add to the problem. But it's generally a pretty well understood phenomenon. But back in the early 90s, there were a series of experiments done in spin polarized hydrogen and in helium-3,4 mixtures, where there appeared some really dramatic departures from classical diffusion. And so the experiments, they basically took a couple of reservoirs of spin polarized gases, connected them together via a narrow tube, sometimes added some magnetic field gradients along the way, and then measured transport coefficients and basically measured what they saw. And they saw over a range of room temperature down to cold temperatures, to liquid temperatures, the diffusion coefficient changed by over an order of magnitude. So that's not a classical prediction at all. But more interestingly, when they took NMR spectra of what was going on in this tube here, they came up with a lot of really long-lived echoes of collapse and revival of coherence and things that persisted way longer than you would expect for any kind of classical diffusion times. And so this was interpreted as the creation of new spin domains in the system, spontaneous creation of spin domains that were precessing around, and there were a lot of complex dynamics going on. But this is kind of the best picture you could do at the time, was just NMR spectra. And so we aim to come in with ultra-cold atoms and do a more localized kind of probe of things. I don't know that I really need to sell the spin part of spin transport to this audience, but nonetheless, obviously spin carries information, and so that's kind of one of the driving things in studying it. But it's also very fundamentally quantum, and so understanding it can open up a wide array of nonlinear, non-equilibrium systems, looking at how magnetism and coherence enters into diffusion and transport and the like. Maybe if you understand these things, then you can start talking about spintronics or atomtronic devices, devices that are based on the flow of spin. And you can think of using cold atoms for transport and storage of spins. If you want to get really speculative, you can think about exploring the coupling of spins with other less kind of well-considered things like spin charge couplings. You can maybe think of coupling spins to phonons in systems or heat or things like this. And this kind of merges into the second sort of branch. One is kind of the understanding the fundamental physics of these non-equilibrium systems, but there's also this device-oriented approach. And I wouldn't say to anybody that doesn't have the prospect of offering me money to do research that I think we're going to make atomtronic devices based on this technology. But I think there are some promising things out there. And there are related technologies that people are working on in ultracold atoms. So I don't want to say that we're going to make any kind of atom-based circuits and things like that, but I think there are some interesting avenues to explore. And this kind of harkens back to the early 70s, where the use of domains in storing information. In the early to mid 70s, magnetic bubble memory was the hot thing. All the semiconductor companies, all the nascent computer companies of the 70s were going all in on magnetic bubble memory for non-volatile memory storage. And it's basically just small domains in various alloys like garnet alloys or related things, where each domain just contains a bit. And you can move these domains through various registers by driving them with external fields, maybe in some permalloy materials nearby. This is actually, I think TI was the first one to make a commercial chip of this, but this is Intel's 1 megabit static memory chip from 1979. I think they got up to about 16 megabits before hard drives came along and just crushed bubble technology. But there were actual commercial devices, like you could buy personal computers, although I think they called them portable computers at the time. They were based on this magnetic bubble memory. And so this kind of died for a while, but in labs and universities, research sort of carried on from a more academic bent, and it's kind of revived in the last decade or so. With the advent of looking at domains in nanowires. And essentially the driving use case for this is that at some point we reach saturation on the information density that you can store in 2D materials, in a hard drive materials kind of setting, or a RAM or something like that. And so the idea is, well, go into the third dimension, and that becomes really challenging to actually access and read. And so one of the ideas is to use domains in nanowires, sort of a return to the bubble memory kind of idea, and then make bundles of these things in 3D to create a much higher information density. And you can drive these domains through through nanowires to registers with various spin torque couplings or field driving or things like that. And so the work that we're doing, I'm not claiming we're making nanowire kinds of materials, but you'll see some of the geometric similarities here. So let's start talking about the system that we're dealing with here. So I want to start by just doing a comparison of the energy scales. So in non-degenerate gases here. So I'm gonna first start with everybody's favorite non-degenerate gas, air, around us. I don't know if it's everybody's favorite. My favorite's rubidium, but everybody else's favorite non-degenerate gas. And I just want to compare the gravitational potential difference between oxygen and nitrogen, just due to their different molecular weights, over maybe a large auditorium, like a 20-meter kind of height. And if we put that potential energy difference in temperature scale, it's about 90 millikelvin. We compare that to the thermal energy, 300 Kelvin. You see a really, really small ratio between the two. And so this is really driving home the point that everybody knows, that if you separate oxygen and nitrogen in a 20-meter room vertically, that they're not going to persist like that. They're going to rapidly mix and reach equilibrium, and it's just a pure energetic entropy kind of argument there. And so you would never expect to see long-lived inhomogeneities in an air system, right? We all know this. This is why we don't spontaneously suffocate in a room, because all the oxygen runs up or down somewhere. Let's do the same thing with an ultra-cold gas. So a rubidium-87 gas cooled to hundreds of nanokelvin, 650 nanokelvin. Two different spins. I'll talk about the states later, but a spin up, spin down kind of thing. These guys have the same weight, so the potential difference that we're talking about would be some kind of interaction difference, a pressure shift or a density or a mean field shift, something like that. And the potential difference between these two spins, they don't have strong magnetic moments, so they don't have sort of iron kind of spin-spin interactions. It's very, very weak. Neutral atoms and no strong electric potentials. So the potential difference is about 200 picokelvin, 0.2 nanokelvin. The thermal energy really cold, but it's still non-degenerate. We haven't dropped below the Bose-Einstein condensation temperature. So 650 nanokelvin. I've tweaked the scales here and the numbers to give the exact same ratio. And so this would say that if I took some kind of gas like you see here with a spin up and spin down, color-coded purple and green, and if I separated them in some kind of ultra-cold trapped gas, that based on this energetic argument, I would never expect to see any long-lived structures in the system. And yet we do. We see something that looks exactly like what's here. These are real pictures of cold atoms. So long-lived inhomogeneities exist in the system, and I just made the argument that it can't be energetic here. So if it's not energetic, let's talk about some other scales. Let's look at length scales instead. So in ultracold gases, we've got a few different length scales that are relevant. We've got the de Broglie wavelength, proportional to 1 over the temperature. We've got their interaction length scale. This is the S-wave scattering length. And this is an effective scale on which two atoms will interact with each other. And we've got the interparticle spacing, so 1 over the density cubed here. These are kind of the main ones. I guess we have the system size as well, but that's not really relevant for us here. And so we can come up with a bunch of different scattering or different interaction regimes by just comparing the ratios between the two of these, or the three of these. Some of these will be familiar. The first one, where the interparticle spacing is much bigger than anything else, and the de Broglie wavelength is much smaller than anything else. This is what we think of a classical ideal gas. So this is just ordinary diffusion. The third one down here, where the de Broglie wavelength is bigger than the interparticle spacing, this is when wave functions start to overlap. This is the regime of Bose-Einstein condensation, or quantum degeneracy. This is when all the particles end up in the ground state, and energy, there's basically no kinetic energy in the system. And if there's no kinetic energy, then you just get phase separation like oil and water based on different interaction differences between the different species. The last one is not what I'm going to talk about here, where the interaction length is huge compared to all the other scales in the system. This is a strongly interacting gas. There's a lot of interesting physics that's in here. This gets you into the unitarity regime, where all the other scales drop out, and you can start comparing with physics that happens on astrophysical scales all the way down to cold atom scales. And you get some really interesting quantum limited diffusion in here, where you essentially have a quantum speed limit. I'm not going to talk about that. But the one that I'm going to talk about here is this kind of new regime that you don't see in a lot of other places. And that's what I call the quantum collision regime, where the interparticle spacing is still really large. So our de Broglie wavelengths are not overlapping with each other in general, on average. So it's a non-degenerate system from that point of view. But the de Broglie wavelength starts to get bigger at cold temperatures, and it can become larger than the interaction length. And once that happens, we have to start considering quantum effects. To see that a little bit more, I've got a little cartoon here where I have a couple of atoms, these two green guys, that are bouncing around in our sample of trapped cold gas, and they come together and they interact. And when they interact through some isotropic S-wave scattering. One of them bounces off with a forward scattered wave, and then one of them then has to recoil in the backward direction through momentum conservation. And I noticed as I was staring at this, these arrows don't actually quite conserve momentum geometrically, but hopefully you get the point. But this is not quite the whole picture, because let me, I've got some interaction length scale A here, the S-wave scattering length kind of drawn. Let me put in the de Broglie wavelength. The de Broglie wavelength is bigger than everything. So on this scale, we have very large fuzzy atoms. and the large fuzzy atoms basically overlap to interact. And then one of them goes forward, one of them goes backwards. Which is which? Well, if they're identical atoms, both happen. Quantum mechanics says that we have to symmetrize the collision. And when we do that, we end up with this two-atom wave function that has an extra term in it, where we have atom 1 going forward and 2 going backward, and atom 1 going backward and 2 going forward. And quantum mechanics says that you have to include both of those in your wave function. Anytime you get extra terms in your wave function, that leads to interference. This is an entangled state. It's not as far as I can tell, it's not a metrologically useful entangled state, but it is an entangled state here. So what that means then is, let's say that our atoms now have spin. And so I'm representing each of these atoms as a spin on a Bloch sphere. And I've put them in some kind of transverse orientation. So some superposition between spin up and spin down here. And maybe they have different histories, so they have different transverse spin orientations, different amounts of Larmor precession. Then what happens effectively is when these two atoms interact and we get this symmetrization that happens, the net result is that it looks like the two spins rotate about their combined spin. So the combined spin is this purple one, and we get then the net effect is that we have these two transverse spins that now rotate into a longitudinal projection as well. And this conserves total spin, but it can change the overall spin rotation. And it's a coherent effect. So if we have a correlation between spin orientation and position, then as atoms move from those positions, we get correlated spin currents. And those spin currents then can interact in a coherent way. This is called the identical spin rotation effect. It relies on the fact that we have indistinguishable particles. It doesn't actually, these are bosons here. You can do the same thing with fermions, as long as you're not down at the Fermi temperature here. And so this requires coherence. So we can't do this with a mixture. We can't do this with orthogonal spin states. But as long as we have coherent superpositions, i.e. this transverse spin here, then we can get this ISRE, this identical spin rotation effect, which can lead to macroscopic collective behavior. And that's what I want to talk about for pretty much the rest of this talk, is the macroscopic collective behavior that we get from these microscopic two-atom interactions in a non-degenerate cloud. So typically, you don't expect to see macroscopic behavior in a non-degenerate gas. Like you shake a bucket of water and it quickly collides with itself and stops. You shake something that has some kind of macroscopic behavior, it can keep oscillating for much longer than you would expect otherwise. That's sort of the analogy that I think about. So I want to talk about two rough classes of experiments. The first is basically to create a spin inhomogeneity. Essentially, take our cloud of atoms, and I'll talk a little more about this cloud, and put it into two domain states with a domain wall in the middle. So we have an up domain on the left side, a down domain on the right side, a narrow domain wall in between, and ask, how does it relax to equilibrium? And are there any metastable configurations that exist? And I wouldn't be asking the question if there wasn't. And this is suggested also by these earlier experiments that I briefly mentioned that happened in spin polarized gases, connecting these reservoirs of spin up and spin down. And then ultimately, though, we don't necessarily just want to make a single domain wall. We might want multiple domains in our sample so that we could think about devices or more complicated spin dynamics. And as soon as we do that, we start moving our domains away from the symmetry axis of our cloud. And as soon as we move it away from the symmetry axis of our cloud or our confining potential, the domain can move. And so we want to ask, how does that domain move? And can we control that domain wall motion? If we can do that, then maybe we can think about moving our domains around in some controlled way to make shift registers for spins, or storing things, or some kind of controlled interaction experiment or something like that. So first, I want to tell you just a little bit about the ultracold gas apparatus. I'm not going to get into the details too much, other than to say we make an ultracold gas. We use laser cooling and evaporative cooling to cool a gas of rubidium-87 atoms down to about 650 nanokelvin. Very cold, ultracold even, but not degenerate. It's about 1.5 times the critical temperature for Bose-Einstein condensation. We hold it in a magnetic trap made of permanent magnets and some electromagnetic coils. The permanent magnets produce a very strong gradient. The electromagnetic coils produce a fairly weak gradient. And so for that reason, we get a 3D harmonic potential, but it's very cylindrical. And so the actual cloud in confinement to scale is this long kind of pencil-shaped thing that's about 38:1 or so. For those that like numbers, the trap frequencies are about 7 hertz by 250 hertz or so. Density around 10 to the 13 per cubic centimeter. So for those of you that aren't used to thinking about these ultracold gas systems, that's kind of on the dense side for these ultracold gas systems. A Bose condensate might be more like 10 to the 14 per cubic centimeter. But for any kind of sort of macroscopic or real world sort of picture, that's very dilute. Air is on the order of, let's say, 10 to the 18, 10 to the 19 per cubic centimeter. And then solids are many times more dense than that. So it's really this light dilute kind of thing that's very slow moving, but non-degenerate. So in many ways, we would expect it to behave like a classical ideal gas. When we put it in a harmonic confining potential, we would expect a Gaussian distribution and that sort of thing. So the spin system that we have is actually not a spin system. It's a pseudo-spin system. So we connect two states via two-photon transition. These are hyperfine ground states of rubidium-87. So it's a nuclear spin flip up and down. We connect them via microwave and an RF photon, and all of the other states then are off resonant and don't participate. So we can reduce the system to these two spin states and just map it onto the spin 1/2 problem. And so then if I say spin for the rest of the talk, you can mentally insert pseudo before that here, but it's not real spin. So I mean, there are real spin states, but it's not a real spin 1/2 system. Their orientation doesn't correspond to up and down with respect to some quantization axis here. Okay, so that's the system. So let me talk a little bit about how we make a dipolar inhomogeneity, or how we make domains in the system. So we've cooled our cloud of atoms to about 1.5 times TC in this magnetic trap. And then what we do is we apply a little bit of light to 1/2 of the cloud. So we mask the laser beam so that we illuminate 1/2 of the ensemble. The laser is off resonant to some excited state. It's the D2 transition. This is not to scale. This our spin up and spin down differ by about 6.8 gigahertz, and this is 780 nanometers. So not to scale. But what it does, what the off-resonant light does, is it provides an AC stark shift. It shifts the energies of state 1 and 2 away from each other, and it shifts the resonant condition. So then when we apply a microwave pi pulse, we have between spin up and spin down, we have a pi pulse on the left side of the cloud, and we choose the intensity of light so that we have an effective 2 pi pulse on the illuminated side of the cloud. So the atoms on the left side flip from down to up, and the atoms on the right side make a little circuit around the bottom of the block vector or block sphere, and they return to their starting point here. And then in between, we have a coherent rotation, essentially a helical domain wall, where the spin rotates from down to up over some fairly narrow distance here. We image these things just by projecting state 1 and 2 in subsequent destructive measurements. And then we can construct the longitudinal spin in parallel, or MZ if you prefer, just by taking the difference between the two. And so there's this overall Gaussian profile to the whole thing, because we're holding it in a harmonic trap. We don't have an inhomogeneous potential, or we have an inhomogeneous potential, not a homogeneous potential. And then you see this domain wall here, where we've got spin up on the left side and spin down on the right side. Very briefly, this is the only equation. It's not the only equation I'm going to show, but it's almost the only equation I'm going to show. I don't want to get into it too much. There is a Boltzmann equation, a kinetic equation that describes how this gas evolves, and it looks very similar to a normal Boltzmann equation, if you're familiar with that, with one difference. So there's 3 coupled equations for the spin density distribution. In parallel, mx, my, mz, or parallel perp, and the phase, if you prefer. So we've got the standard kinetic term. We've got an external potential, the trapping potential there, harmonic magnetic confinement of the atoms. On the right side, we've got a collisional damping term to restore the system, bring the system to equilibrium through elastic collisions. And then in the middle, we have a torque term. This is the one that's unusual. This is the part that makes the quantum Boltzmann equation quantum. And so we've got this cross product that essentially is the spin distribution is precessing around some effective magnetic field. The effective magnetic field has two terms in it. The second term, this Gm, is a mean field shift. So that's the spin that's torquing around as a spin current moves through the ensemble. The spin torques around the local mean field. This is the identical spin rotation effect. This is the spin-spin exchange-driven rotation. There's also a differential Larmor precession, effectively due to any differential potential experienced by up and down spin here. So the way we actually control this effective magnetic field so that we can control the evolution of these spin distributions is by modifying these terms. We can't do too much with this ISRE term. We can modify the coherence of the sample a bit. But this is basically, we're stuck with whatever coupling constant that nature gave us. But what we can modify is this differential potential experienced by spin up and spin down. So first, we want to get rid of the background differential potential, get rid of the background effective magnetic field, and then add our own. So the background comes from two sources. One is the Zeeman shift, differential Zeeman shift. Spin up and spin down don't have quite the same magnetic moment. And so we see some kind of parabolic looking potential from that. And then we have a differential mean field shift, and that's because spin up and spin down don't interact with the same, quite the same interaction energies. And that has a Gaussian potential that's proportional to the density. And so we can tweak things so that we can cancel our parabolic Zeeman shift with our Gaussian mean field shift. It's not quite a perfect cancellation, but it's pretty good. And so this gives us a spin independent potential for our spin currents to evolve in. So we can create an inhomogeneity, and then the potential background doesn't really affect the spin currents other than the spin independent trapping potential that we have. And then what we do is we can create an arbitrary differential potential by just spatially modulating off resonant light. We can spray in patterns of light that will essentially create whatever sort of effective magnetic field that we want. And I'll say a bit more about that later, but essentially we can turn a laser on where we put it on low intensity on one side and we ramp it up to high intensity on the other side of the cloud, and compare that with the laser off. And what I'm plotting here is just this differential potential, which is effectively an effective magnetic field that the atoms experience. And so the blue would be no field, and the red would be like a linear field gradient across the cloud. So we can control the Larmor precession of the spins in a local way. That's kind of the takeaway message here. Okay, so that's kind of all the tools. What actually happens with the dynamics in the system? So here's what we see if we let the thing evolve. So this plot shows the evolution of our 1D spin distribution as a function of time. So this kind of stripe here near time equals 0 is our initial spin distribution, where we have spin up on the left side, spin down on the right side. This is this kind of domain, and we have this fully polarized domain wall. And then it evolves over time. And if you're not used to looking at these things, you're like, okay, I see sort of something. It looks a little blobby and the colors kind of swap. You know, okay, what am I looking at here? First thing to note is that if we calculated, using just the Einstein diffusion relation, calculated what the classical diffusion time is, even for this cold gas, we would get something on the order of 25 milliseconds, which tells us that we would expect any kind of inhomogeneity in the system to just disappear after a few tens of milliseconds. Obviously, that doesn't happen. You can see these structures persisting out to hundreds of milliseconds. The other thing to note is that the atoms are held in a harmonic trap. That trap has a frequency, or a trap period. It's about 7 hertz. And so we would expect atoms to oscillate in the trap. And we see that there is some oscillation where the domains flip orientation, but it takes a long time. It happens at a rate that's much, much longer than the trap period. So clearly the dynamics are not behaving as we might classically expect. To prove that, we can actually remove the coherence from the system. So this is a domain wall where the atoms where the spins smoothly rotate from down to up through some kind of helical pattern. What if we just remove the coherence, and so where the spins just go from down and they shrink and then they point up with no transverse component? So we can blast the middle of this domain wall here with some off-resonant light with strong spatial inhomogeneity. We let atoms move and they very quickly dephase and decohere. And this is what we see. So we remove all of the transverse component and we just have a longitudinal component here. So this is basically a mixture of spin up and spin down with no superposition in there. And what you see is something that's a lot closer to what you might expect classically. The system oscillates much faster and these structures go away. So the key is that there is coherence in this that's giving us this coherent spin rotation effect here. And essentially this identical spin rotation effect provides a certain spin stiffness that through these coherent spin rotating collisions, as spins move to inhomogeneous or to regions with different spin, essentially the ISRE helps synchronize the spin and keep these structures longer lived. We can look at the transverse component. So here I've now turned it sideways for some reason and changed color map because it's transverse. That was on purpose. And so here we're measuring the magnitude of imperpendicular, basically how much coherence do we have in the system, although I'm using that term in a very sloppy way here. And initially you see there's only coherence here in the middle of the cloud, which is what we expect. We only expect to see coherence in the middle of the domain wall, and there shouldn't be coherence out here because we have fully polarized spin up and spin down domains. And then you see it diffuses out. Okay, that's maybe what you'd expect. Diffusion happens. Except if we look at the amplitude of these Ramsey fringes as a function of time, this is plotting the amplitude out to about the first 100 milliseconds or so. And you see in the center of the cloud here, the amplitude doesn't change. Right? The amplitude remains pretty constant, which means that we're not actually having spin diffuse out from the center of the cloud. Yet if you look at the amplitude of the transverse spin on the edge of the cloud, then it increases. It more than doubles as a function of time. So this is not actually diffusion. This is actually growth in the transverse spin. So this indicates that there's actually a transverse spin instability where the sharp longitudinal spin feature is unstable to transverse spin fluctuations. And this is related to something called the Castaigne instability that I don't want to talk about, but it essentially causes growth of the transverse component here. Okay, so let's get back and ask, how can we control this? So this is the same picture that I showed before. This is our two-domain spin structure evolving in a spin-independent potential. So we've flattened the potential spin up and spin down, see no different Larmor precessions anywhere in the cloud. So let's apply an effective magnetic field gradient so that spins on one side of the cloud rotate more quickly than spins on the other side of the cloud. And if we do that, and we pick the right size, then suddenly we see that this two-domain spin structure lives for a really long time. So this is out to 600 milliseconds and it's still alive. This is really surprising. This is more than 40 times the classical diffusion timescale. So we would expect this non-degenerate gas to just go away, these inhomogeneities to just disappear, but it persists. And if you look at this, okay, 50 hertz per millimeter. That's the energy of the effective magnetic field that we're driving. To give you an energetic comparison, the thermal energy of a 650 nanokelvin cloud here is about 14 kilohertz. So this energy that we're providing from the effective magnetic field is truly tiny compared to the thermal energy. So again, this cannot be an energetic argument. And just to prove that we understand what's happening, if we reverse this magnetic field gradient and we turn it the other way, then instead of stabilizing these domains, we actually make them go away faster. So essentially what's happening here is that by providing this effective Larmor field gradient, we're making a phase gradient in the transverse spin. We're controlling how the transverse spin moves. And if we choose that right, and if our density and temperature is right, when a spin moves across the domain wall from up to down, then it can effectively do kind of an adiabatic following, where it, as it moves, this identical spin rotation effect makes the spin always kind of torque and follow around the local mean field. And if we give it just a little bit of extra rotation from this external effective magnetic field that we're driving, we can perfectly match that, so that an atom can just uniformly go from spin up and kind of torque its way down and go to spin down by the time it finds itself in the other domain. Essentially, we're driving extra spin currents through this applied field that are balancing the diffusive spin currents, that the diffusive spin pressure that wants to make this structure disappear. Okay, I think maybe in the interest of time, I'm going to skip the transverse spin. Actually, no, I will talk about the transverse spin because it's kind of interesting. So if we look at what's happening to the transverse spin in the middle of the domain here, again, we only really have transverse spin in the domain wall because our domains are otherwise largely polarized spin up and spin down. So there's not really any transverse component. So here's just a projection where we've got the red as the longitudinal spin with our up and down domains. And then the green is at short time t equals 0 here is the amplitude of the transverse component. So the transverse spin starts out in the domain wall and it stays in the domain wall because we see this domain wall not really move, other than there's a little bit of motion here due to loss in one of our spin states. But what you see here, if we look at the phase angle of the spin, so this is zooming in on this center portion, looking at the phase of our Ramsey fringes, you see oscillations, and I've drawn a couple of lines here to help kind of guide the eye. So we have spins on one side of the domain wall oscillating in one direction, and on the other side of the domain wall oscillating in the other direction. So what you're getting here is, this is a transverse spin wave. So the transverse spins are oscillating back and forth like this in the middle of the domain wall, while the longitudinal spins are doing absolutely nothing. They're just sitting there in stable domains for 600 milliseconds or more. And so this is a decoupling of the dynamics between the longitudinal spin and the transverse spin. But yet the longitudinal and the transverse are required to cooperate together through this identical spin rotation effect. So this is kind of an interesting phenomenon. It has a little bit of overlap with spin charge separation, but not too much. There's some similarities there. And so essentially, this is a decoupling of the dynamics between the two in a way that you wouldn't normally expect. I'm going to skip the characterization of the steady state domains. You can ask me about it if you want to know. We have some predictions. We understand them for the most part. But I want to get to the asymmetric study here. So this is more recent work that we've been doing. And essentially, we move a domain off center. And as soon as we move it away from the center of the trap, as I mentioned before, it can move. It's not, we've broken the symmetry, it now might have a preferred direction. Here also, we've added some improved domain creation technology. So we use digital micromirror devices to create our patterned light, our structured light, if you will. For those not familiar, DMDs or digital micromirror devices, they're the chips that power digital movie projectors. It's the exact same technology made by TI. And it's essentially an array of little MEMS mirrors that you can turn on and off with electrical pulses at a very rapid rate. And so we can make patterns. We can draw whatever pictures we want and project those in some binary way onto the atoms. And this picture here in the lower left, whenever I look at this always looks to me like a Photoshop, like I've just Photoshopped SFU on there. Somehow the contrast of that looks like a Photoshop, but it's actually an image of the real DMD, where you can see we've turned some mirrors on and off there, and you can just see some room lights reflected off of there. So what we do is we make patterns on that we might like to project on the atoms, and maybe some kind of gradients or things like that, or sharp cutoffs, masks, and things like that. And then we just image those on the atoms, and that's our way of giving a very fine-grained control. And so just to show that we can do this, we can make 3 domains. This is slightly older data, so you can see some of these fringes are just imaging artifacts here. We can make 3 domains, and if we let it evolve in a spin-dependent potential, then we get spin waves. This is sort of a well-understood phenomenon why it oscillates back and forth here, but again, it's this identical spin rotation effect without bothering to control the effective magnetic field. But we can control the effective magnetic field. We can apply 2 effective magnetic field gradients, essentially a V, that kind of right across the middle to stabilize each of the domains. So it works for multiple domain spin structures. We can also do things dynamically. We don't have to let the system evolve in a static potential. So here we're back to 2 domains, but instead of just letting it evolve the whole time, we can flip the domains. We can let it evolve for 100 milliseconds or so, and then flip the effective magnetic field. And you can see that we can suddenly destabilize it. And so we can do dynamic control, which then opens up the door to maybe trying to do some kind of dynamic manipulation of spins, maybe for a spin device or something like that. So let's talk about how these off-center domains move here. So here's an initial profile where red is the projection of the spin up, blue is the projection of spin down, green is the difference between the 2 or the longitudinal magnetization. And that's kind of my little cartoon down here of our 3 domains with our narrow domain walls. And we let it evolve. So same thing, this up, down, up domain is evolving as a function of time. And first, you might notice that the quality of the data is much better. We've learned to clean optics and control our potentials and improve our imaging over the time. But also things are kind of interesting. You see multiple domains. So our initial 3-domain structure, first, it's fairly long-lived as well. We still have this identical spin rotation effect that's helping to synchronize spins. But then you see also there's regions where our 3 domains, there's times where the 3 domains split into 5 domains. So we have a creation of a new domain and a bifurcation of the middle domain. And if you stare hard, you can convince yourself that these domain walls actually move. And we can extract these domain wall positions. So this is the left domain wall here, and I've zoomed in. We can extract these positions. The blue line is just a bit to guide the eye. And we see that the domain wall moves a bit and then gets ejected from the cloud here. So there's a lot buried into extracting the domain wall positions here. That this is the second equation and the only other equation that I'm going to show. We extract the domain wall positions initially just by fitting some phenomenological function. So some hyperbolic tangents, some stair-step functions with a Gaussian to give us the overall density structure. That works really well at short times. We have really high signal to noise. However, this model kind of fails once we get 5 domains. Okay, we can multiply more hyperbolic tangents in there. At some point it gets a little bit hand wavy to do all of this, and the signal to noise starts getting kind of bad as the domains move out. Your eye is much better at picking out structures than an actual fitting algorithm is, it turns out, when looking at these. So this is not the best. So what we've done is we've developed a binary threshold algorithm where we essentially just binarize the image. And with some threshold around 0 spin and 0 longitudinal spin, and we pull out the domain walls, and you can see where the signal to noise goes to heck. And of course, that's not real out there. And you can see the creation of a new domain coming in. And then I'm mostly going to focus just on the left domain wall here. And so we can pull that out and kind of zoom in. This has been interpolated just to make it a little prettier, although you might quibble as to whether that's pretty per se. But in general, we don't use interpolated data. We use the actual points that we measure here. So one thing that we might do is we might ask, how does the domain move? So we can look at its velocity. We can just take a finite difference kind of approach and look at delta z over delta t from each of our steps. And you can see something that looks like this. These are a number of different preparations where we move the domain wall around a little bit in the cloud. And you can see it kind of doesn't move that much, and then it eventually takes off, and at some point it hits the thermal speed limit. So I'm displaying the motion of the domain wall, essentially the derivative of this, the slope here, or that slope, the derivative of that line, scaled by the thermal velocity here. And So you see there's some kind of thermal speed limit. I wouldn't take this point, take every point at the end of a graph with a grain of salt, so-called Fermi points. Never trust the last point, because if people could go farther, they would have. Okay, so we took some higher quality data with some different preparations. And looking at this, then we see that there's kind of two regimes of domain wall motion here. That there's some low velocity kind of motion. We see some negatives, a bit of positive, a little bit of motion in here, and then it really kind of takes off here. And we have some understanding. This is definitely still work in progress, but on the slower side here, the left part, this we interpret as basically spin torque driven motion. This is where the identical spin rotation effect, this exchange scattering driven motion, is really playing a key role. And this requires a lot of coherence for us to have these identical particles for the ISRE. And essentially, this is giving us this kind of spin stiffness where you don't see a lot of motion. But eventually, diffusion or kind of a momentum-driven behavior takes over and determines the longer-term trajectories. I'll say a little bit more about that in a second. But first, I want to say, can we, ultimately, we were talking about, can we control these things? So can we alter the domain wall behavior? So we tried just moving the domain wall around. These are different initial positions in the cloud, and we see very different behavior. Some of them show this kind of, a lot of the in-between region shows this kind of curving behavior. This is delta Z, so they actually came from different places. So the blue one would be closer to the middle of the cloud. The red one the main wall was closer to the edge of the cloud. And these seem to mostly just have this kind of diffusive driven behavior. And so we're like, oh, okay, so it has to do with the position of the cloud. And, if we don't have enough spin of the other, of both types, then we just get kind of diffusion and the domain wall just kind of crunches and disappears or gets kicked out of the cloud. We take higher quality data with improved domain preparation, where we're really taking care with our polarization and the like. We see, well, maybe that's not actually the case. That, if you stare at these curves, you'd be hard pressed to see a significant difference between them. And here I've taken out the delta Z, and you can just see they're starting at different places, and they all bear basically the same kind of shape. So it seems like it doesn't actually depend all that much on the position of the domain. So what's driving these different behaviors then? Well, we determined through careful choice and accidentally bad preparation, a bit of both, that actually, if we change the polarization of one of the domains, so basically rotate the spin a bit in the center domain, so it's no longer up, down, up, but it's up, kind of down, and up, then we see very different behavior. We start seeing this kind of curvature here, more of these sort of sickle kind of patterns where it curves in a bit and the like here. So this is telling us that the initial polarization is probably a key role here. So we did a more careful study of that. And basically, when we create these domains, we apply our off-resonant light in the middle of the cloud, and that creates this effective 2π pulse here that gives us a perfect down rotation. But if we just change the intensity a bit, then our perfect 2π pulse becomes 2.1 pi, 1.95 pi. And so instead of getting a perfect return to spin down, we end up with something at some angle here. So instead of making up, down, up domains, we make up some angle down, up domains here. Still fully coherent. And you can see that here by the longitudinal projection of the spin then changes here. And as we do that, we're able to smoothly tune the motion of the domain wall, all starting from basically the same position, but essentially adding more transverse spin to the domain shifts the behavior. And instead of just kind of driving the behavior out as diffusion, he eventually takes over. It actually pulls the domain wall into the center domain for a little bit before diffusion pushes it out. We're still fully trying to get a phenomenological picture of this, but essentially we think of it as by changing the polarization in the center domain, we're disrupting the balance of spin currents at the domain wall. We're disrupting the amount of spin up that's moving across the domain wall and spin down that's moving across the domain wall, and that causes the domain wall to move. But also by adding more transverse spin into this middle domain, we're getting more of these spin exchange collisions, so that also can alter the behavior as well. In the interest of time, I'm going to skip transverse. No, I'm not going to skip transverse spin. I'm just going to say that there's one further control that we have, and that is to look at the phase of the transverse spin. So what you see here is kind of what you've seen before with one domain, but now we have two domains. The initial transverse spin magnitude is largely confined to the two domain walls. It shows some pretty complicated and interesting coherence evolution effects that I don't really want to talk about because we don't understand that very well yet. But what I want to point out here is here are two different preparations of the transverse spin where we've just tweaked around the light that we make the initial spin profiles with. And one of them has a fairly large phase gradient across it. So the spins in one position differ from the spins in another position by about 2 radians or so, whereas another has a much smaller, it's much smoother, so maybe only about half that, 2/3 that. And if we look at the evolution of the two, we see a very different evolution. The longitudinal spins in both of these cases looks nearly identical, but the long time evolution of the two differs dramatically. And so the initial behavior, very similar, but at longer times, it seems like the actual orientation of the transverse spin, not just the amount of the transverse spin, but its orientation plays a key role. And essentially, our understanding, very hand-wavy, is that these phase gradients can inhibit or enhance the formation of spin currents. That this kind of goes back to the same sort of phenomenon where we create these phase gradients to stabilize domains earlier. So these sort of inadvertently created phase gradients can stabilize things or enhance the ejection of the domains from the cloud. So this is another thing that we want to look at and control more. I just want to say we have compared with Boltzmann simulations. It agrees reasonably well, but not so much at long times. And I think that comes back to this, really understanding kind of the exact phase profiles and how that determines the evolution. I want to, in the last couple of minutes, briefly talk about what we can do with this information. So we've started to get a handle on what the parameters are that control the motion of the domain wall. The polarization of the domains, the phase profile, the coherence that's in the domains, a little bit the position of the domains. I haven't talked about density and temperature, but those can have an effect. Let's say we want to create a device where we move these domains around in some kind of controlled way, maybe make some kind of, domain shift register or something like that. How do we do that? We've got a Boltzmann equation that pretty accurately describes the system, but it turns out that trying to figure out what input parameters give us desired behavior is really hard. The inverse problem for this is nigh on impossible. Parameter space is just way too large, especially if we add dynamic control, where we want to change the effective magnetic field as a function of time and space during the evolution. So it's just too hard. So we can get a computer to do it for us. And the idea then is to use machine learning to do that. And so we take our Boltzmann equation, we use high performance computing to generate thousands of trajectories. I think there's about 1,900 trajectories here. These are all a bunch of just different domain wall trajectories here thrown on top of each other. And then we throw those into a neural network and we train it on these. And it does its convolutional magic. And then we take a sample input trajectory. This is actually a real trajectory. It's a little bit boring, but it's a trajectory nonetheless that we've generated from the Boltzmann equation. It wasn't in the training set. It's not one of these 1,900 images here, or 1,900 trajectories. We throw that into the model, and we have the model tell us what input parameters would give that trajectory. And it does that. So here's a zoom in a little bit so you can see the match a little bit better, where the red is the model result. So our machine learning model has told us, use the following coherence, use the following domain wall position, use the following domain wall polarization. We take those parameters, we throw them into the Boltzmann equation, and we generate this red curve. Okay, it's pretty good. Now since we're doing machine learning, we should prove that it's actually learning and that it's not memorizing. So we pull out the best match from the training set and see, could we have just done the same without even training it, just done the best match? And Well, the best match is pretty good, this purple curve, but it's not actually a true match. It's not as good as the model result. So the machine is actually learning. The best match would get even worse if we reduce the size of the training set. And we try some other trajectories, maybe more interesting ones. And again, the model result is almost dead on the target trajectory. We look at the best match. The best match, again, is pretty good, this purple one, but it still is not as good as the machine learning model. And so these are pretty recent results. We haven't done a lot with it since then. The next step, in order to get something useful out of this, we really need to optimize the model. This training set here has a small number of parameters. We'd really like to use a large number of parameters to really control everything. But the larger, the parameter space increases exponentially as you add more parameters. And so we really need to make the model run efficiently, or figure out which model, which parameters we actually care about. Maybe we don't care about matching whole trajectories. Maybe we just want to say the domain wall starts here. I want at some point in time it to end up at this different point here. I just want to move it. I want to move my domains to control the flow of information or something like that. That might be an easier problem that might require a smaller parameter space there. And so then with that, I'm going to end. I'm going to quickly flash forward to the group. The work has been done by two fantastic graduate students, one of whom is in the audience. I can embarrass her. Olga Ferran has been doing the lead on collecting the data and analyzing it and understanding what parameters control spin. And Mehdi Porzan has been leading the charge on the machine learning project and working with that. And we've had some theory support from Bob Reagan and some past people. And I will flash back to the summary and outlook. But basically, the summary is that even in classical gas, so-called classical gases above degeneracy, they can still be quantum in this ultra-cold regime. We can see these coherent exchange effects that drive macroscopic behavior in an otherwise classical gas that all come from exchange symmetry in microscopic two-atom interactions. And this can drive macroscopic behavior that we are understanding and beginning to learn how to control. And with that further control, we can study the hydrodynamics of the system, make better predictions using machine learning, and possibly maybe make some spintronic devices, control transport, or put together spin diodes and transistors and things like that. So thanks for your attention, and I'm happy to take questions.
Any question?
Will the domain wall persist if your system is 2D? So yeah, because it looks like for most of this presentation, the domain wall is like roughly like one-dimensional and initialized.
Yeah, so that's a good question. So if you couldn't hear that online, the question was about 2D domain walls, and I didn't really highlight it, but our system is effectively 1D because it's this long thing, and the trap frequency in the radial direction is faster than anything else, and so everything averages radially really fast. So it's an effective 1D system, which makes it really nice for control and for theory. But I mean, 2D is bigger parameter space, and that's possibly more interesting. The energetics change. You definitely get you get all sorts of spin wave modes and this kind of thing in 2 dimensions. Stabilizing things becomes a bit harder because there's more modes that the system can decay into, but certainly it's possible. We'd be happy to do that. We're a little bit hamstrung by the fact that we have permanent magnets in our magnetic trap, and so you can't really adjust those very much. But I think that's a very interesting way to go in the future, is expanding parameter space. Yeah, I mean this makes a nice analogy with 1D nanowires, but there's no reason to confine ourselves to that. Yeah.
Okay.
Another question? So I'm not so sure I asked that before. Because when you talk about, say, you have a domains, and then those domains are not just diffuse away, and it seems that it can actually make the domains more stable and having no quantum effect.
Yep.
So can I understand it in terms of the signal effect? Say if you have something that is coherent, say if the angle is change a little bit and then you do a measurement, so that basically stabilizes the state. Is there any?
I mean, it's certainly analogous to that. I'm
Yeah.
not sure that I would have to think hard as to whether that's a deep analogy.
Yeah.
But
Because
I
that
mean,
is a bit surprising, say, if you have coherence and actually slow down something and it's decoherent and actually that move fast. And the only thing that I know have that is that maybe quantum Zeno effect.
yeah, I mean, it certainly does make me think of quantum Zeno things, which is, also why I mention, I think of it kind of as an adiabatic following of the spin as it precesses around.
Yeah.
I mean, I can't quite think of it as, I can't quite wrap my head around thinking of it as a measurement.
Okay.
Though, and I will say that ultimately what limits the lifetime of these things is the spin inhomogeneities that you put in the system to start with. That ultimately, there are elastic collisions, randomizing elastic collisions that occur. And if you have some inhomogeneities, then over long times, eventually those will average out and decohere. And once you get decoherence, then it becomes fully classical, a binary mixture, and it can't support anything.
Yeah.
But yeah, I'd have to think more deeply about it as a measurement problem.
Yeah, question. I have one quick question. So do you think it will change if you change the size of the cloud? Say if a longer cloud or a shorter cloud, do you expect that the whole physics is actually the same, or do you expect?
Yeah. So the question is about the size of the cloud. Yeah, I mean, actually, I would love to make a really huge cloud so that it looks a bit more like a like unbounded diffusion problem. And a lot of the theory for looking at these metastable spin states for the metastable domains actually approximates it as the domain wall as much smaller than the size of the cloud and just treats it unbounded. And the theory starts to break down as the cloud gets more on the size of the domain wall. And you saw the domain wall is not as small as we might like. It's not negligibly small compared to the size of the cloud. I mean, I think for a lot of the data we're using domain walls on the order of like 70 microns or so. And the Gaussian full width is like 350 microns. So I don't know, call the cloud size like 600 microns or something like that. So we're on the order of like 10% anyway. And that becomes significant enough that, you have issues. I mean, I would also like to not have the Gaussian distribution. And so that you get from just the trapping potential. And if you make the thing really big, then that becomes pretty flat.
Oh, yeah.
So from that point of view, yeah, I think it's, and one can do these things. There are people that use these digital micromirror devices to essentially sculpt potentials and hold atoms in boxes, basically using repulsive light to kind of carve out the potential and flatten it. And so we could do that. We would need more lasers and more money, but it's certainly possible. Yeah.
Okay. One last question.
So for the pseudo-spin exchange, how is it done? Like for the two pulses, are they just sent in simultaneously, or are they sent in?
The two pulses.
So for the pseudo-spin,
The
ground state.
Oh yeah, simultaneously. Yeah. So although they don't really need to be, so you can. Let's see if I can go here. No, can't. I mean, if the cloud is spin polarized, it's all spin down. It doesn't really matter if you turn on some off resonant light or not. There's no phase that you're winding up. There's no precession about an effective mean field. But basically, we just turn on the light. So immediately shift the resonance condition and do a pi pulse at the same time. And then we turn off the light and we let it evolve in either a spin independent potential, or we turn on the light in a new pattern. We put in a program in a different pattern to the DMD and then give it some different potential to evolve in.
Okay, so that's thanks, Jeff, again. very interesting.